considering. In the past, we've talked about our orbitals having different shapes. We know that s orbitals have this spherical shape. P orbitals have this weird water wing sort of shape. And if we get into our friend D, we get these weird flowers and all sorts of craziness. So if you were to think of one atom, for instance, let's say phosphorus. So phosphorus has an S, and it's got 1 p orbital, 2 p orbitals, 3 p orbitals. And if we go back to our Vesper model, and we know that things end up being, well, if we were to look at phosphorus, and let's say it paired up with or bonded with some hydrogen, our Vesper model would tell us that there's this non-bonding pair hanging out up here, and that my hydrogens would distribute themselves like so, and this would be a trigonal pyramidal shape, which is based, if we didn't have that non-bonding pair, it's kind of based off of a tetrahedral shape. Maybe not my best tetrahedron, but so tetrahedral. But how can we get a tetrahedron out of this mess? And the way it happens is that orbitals will hybridize to form new shapes in order to allow those 3D shapes that we see in Vesper models. So one of the ways we can explain hybridization is first by looking at some of our elements that like to just change up where their electrons are in order to form more bonds. So some of those we can look at are beryllium, boron, carbon. So if we look at beryllium, remember that beryllium starts with 2 valence electrons, boron starts with 3, carbon starts with 1, 2, 3, 4. So in order to form 2 bonds, one of beryllium's s electrons, it starts with 2, jumps into a p orbital. So I'm going to circle this one, and it's going to jump in there. So we now have 2 orbitals occupied. Notice how there are electrons in 2 of my orbital boxes. And those types of orbitals, we have one s, so it's an s, and a p. So we have now made, so since what is happening is we're mixing s and p orbitals together, we call this, these are sp hybrid orbitals. And we made 2 of them, and it's just plain old sp because we only used one s and we only used one p. Now if we look at boron, so I'm going to just draw what it looks like after the jump. So now it's 3 electrons. So actually the Lewis structure ends up looking like that. So there are now 3 orbitals available for bonding. One of them is an s, and now that there are 2 p's being used, we call these sp2 hybrid orbitals. And we have made 3 of them. If we look at carbon, now remember, carbon can form 4 bonds. So that means we're going to have a total of 4 orbitals. And so these are called, since there's an s, there's P. So there's an S. And then there are 1, 2, 3 p orbitals being used. So these are sp3 hybrid orbitals. Hybrid, not hydrid. So now that these electrons have redistributed themselves, it's much easier for them to bond. So if you were to say to look at carbon, which would have an s, instead it would have been distributed like this, with this s orbital here and a p. Maybe I'll do different colors. So this s orbital might be red, and this p orbital going up one axis might be blue, and this other p orbital going here. How the heck does it make a tetrahedral shape? Well, when those hybrids are formed, what happens is now carbon forms orbitals that look like this, where there's a big lobe and a little itty-bitty lobe, a big lobe and an itty-bitty lobe, a big lobe and an itty-bitty lobe, and probably another big lobe hanging out the back. This looks a little funky, and an itty-bitty lobe here. So that now 4 bonds can form, and it's very easy. So say if you have a hydrogen which has its s orbital, it's very easy for this s orbital to sort of overlap with this large part of this sp3p orbital. If we want to look at some of our other crazy ones with our expanded octets, for instance, if we were to say, look at SF4. Now, sulfur has an S and P normally. 1, 2, oops, opposite spin. 4, 5, 6. Okay? So when it hybridizes, so if it's SF4, then we need to bounce one up into a D. So I've got a D here, this electron jumps into here. So now I am occupying 5 orbitals. How many of each? I have 1 S, I have 3 P's, and I only have 1 D. So I have 5 of those orbitals. And if you remember looking from the shape, if we have 5 of those orbitals, we get a shape that's trigonal pyramidal. Now these 2 electrons, even though they might be non-bonding electrons, they'll still form that hybrid shape like this, okay? Just so they can distribute themselves in a way that will work with the distribution of the other electrons when this bonds. If we were to look at SF6, well, this time, those 6 valence electrons are all completely separate. I actually should draw the whole energy level for subshell for D here. 1, 2, 3, 4, 5. So in SF6, all 6 of the valence electrons of sulfur are separate. So in this case, we have 1 S being used. We have 3 P's, so we have a P3, and now we have D2s. So it's sort of like, and there are 1, 2, 3, 4, 5, 6. 6 of those total. So this is an sp3d2 hybrid. And the shape of this is octahedral. Or at least the shape that it is based off of will be octahedral. Okay, so moving on to electron